Hey there, Mission Control. Well, I've continued to do quite a bit of analysis here in the Martian lab, if you will. And I got my buddies in here today giving us an update. Here's Bandit. Sophie are here. Wanted to talk to you about what I have been working on and that I have a problem. So I've been spending a majority, actually all my time, working on thermoanalysis. You got heat transfer. This is the best book that's out there that I have. Mechanics of materials, very important to have that one. Fluid dynamics, got to have that one. Fundamentals of thermodynamics, that one's pretty important. And then all my math books, including linear algebra, which has been very important. So for all the kids that are watching right now that are in college, don't get rid of your books. They're very important. This book I had to buy, actually. You can see it's dog-eared quite a bit. If you're not familiar with thermodynamics, essentially it has to do with the movement of heat. And for me specifically, what I needed to figure out is how does heat move throughout HAB2, the Phoenix. So you have three methods of heat transfer. Convection, which is heat transfer caused by the movement of air. Conduction, which is the heat transfer caused by, solids touching each other. I can feel the heat because my thermos isn't as well insulated as it used to be. And then radiation, which is heat transfer from all objects that are above 0 degrees Kelvin. That's absolute zero. All objects give off heat. Those are the videos that you see, like the Predator, where you get the infrared and it's showing you all the cool stuff from the movie, and you can see in heat. That's radiation. It's other things as well, but combination of all three. But radiation is a nice way to think of it. So I've been able to get my model, which I've created in Excel here. It's about 285 megabyte file. It's big, and it calculates every second of a day. And I'm going to show you that here in a moment. But I've been able to get it to align with what SolidWorks says. SolidWorks has a thermoanalysis and a computational fluid dynamics module in it, and I've been able to get it to align with the convection and conduction aspects of things. So the basic hand calculations and what the computer is saying, I've got those things to merge together. The problem that I have is radiation. Radiation is a lot more complicated, and the equations to solve radiation end up being a fourth degree polynomial, which is extremely difficult to solve by hand. It actually ends up like taking up that much paper and writing it very, very small. You can look it up. I think it's called a quartic polynomial, and not something you're just going to take on by yourself and do 86,400 times, which is how many seconds there are in a day. So what that means, the problem that I have is I can't really solve the radiation input and output of the system by hand. So I need to have a computer to do it. I've tried though. I've come up with methods. Other people smarter than me have come up with methods that I've used to estimate it, but I'm still coming up, I'm like 4 or 5 degrees off of what the model is saying, and that's really not that bad. But the radiation ends up having spikes when the sun is moving. So if this is the HAB here, then the sun, moves across it. Obviously right here, it's right on top of it, and going through, there's a clear roof on Alpha Pod, which you haven't seen yet. But that radiation comes over from the sun and hits it, and that's going to be really, really hot in there as that radiation comes through. Now I'm looking at trying to model panels that reflect infrared, so that as soon as the infrared from the sun hits it, it's reflected back and it doesn't go into the system. Now this is very important because it helps determine, it determines the size of the HVAC system, which we're going to be using a mini split heat pump. And it is the most efficient way to move heat, both warm and cold. So we're going to be using one of those, and the bigger they are, the more power they require, and the more power they require, the more solar panels we require. And it's just like a spaceship. If you change one thing, something else changes. So I want to spend a lot of time doing this analysis and getting it right. If you recall, if you've been with me from the very beginning, I did this analysis before. Actually, there was a spreadsheet I used a long time ago, quite a few years ago, for HAB1, and it told me I was going to have a power problem, but I was I was in tunnel vision, and I was like, no, that won't happen. I probably made a mistake, you know. I didn't make a mistake. The math was right, I was wrong. I did the math, but I didn't believe it. So this time around, we're gonna make sure we get all the math just right. So let me show you here on the computer. So this is my Lenovo ThinkPad P50, and what we have here is the this is actually the model's running, the analysis is running right now. And let's see here, this chart here is for the actual solar input coming in. So right now I have it turned off. This has to do with the panels that are on the outside of the roof and on the inside of it, because I'm worried about those panels getting so hot that they melt. And then down here we actually have a few things. We have fan velocity, heat source temperature, and what was the other third one here? And the inner temperature. Actually, I can remove that here. You don't want that fan velocity on there. That's kind of confusing. So here we go. Heat source temperature is the big one. Inner temperature is this one here. So what we're seeing is it's very cold. Those spikes to the negative, that doesn't make much sense. So we'll keep an eye on that. Probably just a calculation moment. And then here we have the fan velocity, because we want to know how much air is being moved around. And then up here we have actual thermo showing how hot, how cold everything is. So here we can see the scale. So outside is 109 degrees Fahrenheit, which is our max design temperature. And then we have a heat pump right here, fan unit. And we also have, up at the top, we have a ceiling fan, which is very difficult to see. You might be able to see a little bit of contour. If you see the mouse, there's a little bit of contour of heat right here as it blows everything around. And then down here, it's telling me kind of all the statistics. It says CPU time since the last iteration, and it's 1 minute and 4 seconds. Now, 1 minute and 4 seconds means that it takes 1 day to run an entire day's worth of simulation, because I'm calculating 60-second time steps. So I actually reached out to the folks at Go Engineer, who are the providers of SOLIDWORKS for me, and they're great folks. And we actually went through my computer. They logged onto my computer, they checked everything out, and we figured out every way that we can make the model as simple as possible to get it to run faster. And the bottom line is this computer can run this fast, and that's it. So the computer is really, really good. I love this computer. If you remember, I got this computer when I first started on YouTube to help render everything and do all this work. But even in the few years that it's been, it's already getting too old. So they said, if you want it to go faster, you're going to need a new computer. So let's talk about why we want it to go faster. Well, I got like 30 different iterations that I need to go through so that I can make changes and then run the simulation and see how things are impacted, because my hand calculations are not exactly lining up with the very detailed computational fluid dynamic calculations that SOLIDWORKS is going through. So it's doing three-dimensional analysis with a whole bunch of different variables, the sun, the outside temperature, in 3D. So every way, and all the material properties of the panels and the outer walls and the insulation that we have in there, which I haven't shared all those details with you yet, but I will. It's all in SOLIDWORKS, so it's extremely detailed. It has the better answer. Now, the biggest thing that could be happening is maybe I have it set up wrong. So I'm going to be walking through the model again with the folks at Go Engineer, and they'll make sure that I've done everything right. And so far, in the phone calls with them, it seems like I have everything set up correctly. But what I'm most worried about is that infrared reflecting panels. Did I get all the material properties put in there correctly so that it's actually working? Because what it ends up saying is like it's everything's just getting too hot. So let me show you the hand calculations here, and then we're going to come back to this three-dimensional math problem and the 1 minute thing. So on this screen we have the actual thermal model, which is the hand calculations, and it's big. If I scroll down here, you can see everything changing. These are a lot of calculations, and when we get to the very bottom, there it is, 86,422 lines of calculated equations. So let's just walk through this real fast, kind of see what's happening here. First, you have your value sheet. this is all your inputs. So you have your support structure. These are all the kind of the set variables here, and then you have your heat pump information. I have a few different ways that I could look at heat pumps. And then we have the density of all these different materials, specific heats, thermal conductivities that you have to go look up. When will the material fail? Convective heat transfer coefficient that has to do with convection. Thermal emissivity, that's how much radiation it will accept or reflect, if you assume they're equal. There's a lot of technical stuff I'm breezing over here, so don't get all upset for those that are really in this field. And then you have your basic equations here that are really what set up everything. I have a calculations tab, which I already showed you. And then we have a few different things here that are actually going to summarize it. So here's a surface temperature, looking at the hot profile, just zoomed in there. We see as the sun comes up in this model, it gets really, really warm. It's up to 140 degrees Fahrenheit. So that is pretty hot. We have the inner temperature. Oh, this one broke. I got to fix that. This one's actually very interesting. So what I did to get the outside temperatures, I didn't just want to set them steady. I wanted to actually go and get a bunch of different actual real-world values. So what I did is I went to, I think it was AccuWeather, and I pulled up a cold location and a hot location, and actually typed in all those values, and then I created equations which allowed me, trend line equations, which allowed me to use that in the model. And then I did the same thing with the sun. I actually created a sun model of my own using the total watts per meter squared that's coming in for when it's cold outside as well as when it's hot outside. And that allowed me to create some different equations that I use in the model, which then I bring over here. And the very first thing we do in this model is we set up all of our initial conditions. So outside temperature, and then all the different material temperatures. The sun model information is next. Then we go into the roof, the air gap, the inner wall. I'm just breezing through this so you just kind of get an idea. Here's the sun model for the side walls because they're going to be different offset from the roof. And then we have the beams. Sorry, again, just going through this real fast here. The inner walls, everything coming into the air space, and then the heat pump itself. So I breezed through that. Like I said, that's a huge spreadsheet there. I just wanted to give you an idea. I'm spending a lot of time trying to make sure that we nail the thermodynamics here, the heat transfer, and get it just right so that the materials are have a nice long life. We don't, getting them right up to their failure point or their softening point is not a good idea. And then we want to make sure that the heat pump is as small as we possibly can get it, because that just means we have to produce less power. So there's a lot of balancing that we have to go into all this, and the heat transfer is the biggest consumer of power. It's 4 times more consumptive than light. Something that we really got to get figured out. So on that note, back to what the folks at Go Engineer told me, and they were really great. Again, they logged onto my computer, they checked all my specs, and like, yeah, it's a good computer for SolidWorks, but if you want to run CFD, computational fluid dynamics, and you want to have it be less than a minute per iteration, then you're going to need to get a better computer. So I said, well, what kind of computer am I going to need to have? How big is it going to need to be? And they're like, well, you're going to need, the best graphics card you can afford, and then you're going to need at least a like 3 to 5 gigahertz machine, which you can't get in a laptop. So I actually have a new ThinkPad, the P53, which we're going to be opening up and getting all set up here. And then this P50 is going to be going to a friend of mine who's going to be helping me out with SolidWorks. So going to give him a computer that can handle just doing SolidWorks, so he can help me there. And then my computer will be big enough to where it's VR capable. This one has an external graphics processor to make that possible. But the new one will take its place, and I will be ready. I can go mobile, I can go do the sales pitch, I can get people in the VR, I can do that all on the road and have it all on my workstation. So I'm very excited about that computer, the P53. But that doesn't solve the problem that we need for computational fluid dynamics. So what we have is a new computer in all of those boxes. Well, here's the P53. there's Bandit over there. Hi, Bandit. Hey there. Say hi, everybody. Here is the new computer that we are going to build. Yeah, we're going to build it. So actually, this was told to me by a subscriber a long time ago. It was like, don't waste your money on buying other people's stuff. Build your own. This time I did. This time I'm listening to that person, and we are building our own computer. It is a Pentium Intel i9. It's initially, I think it's 3.5 gigahertz. It's the 9900K series, but it can be overclocked up to 5 gigahertz. But if you overclock something, you get a lot more heat. So we have the Corsair professional grade water cooler. We actually have a car radiator, as I like to say. If you're not familiar with computers and you are with cars, then we actually have a car radiator inside of this thing. It's a water cooled system that other people have overclocked. Actually, I'm not a computer builder, so I don't want to pretend like I'm something I'm not. I went onto YouTube. I found exactly the type of computer that I wanted. Based on what I was told I needed, and somebody had already built one, so I followed their instructions. I watched them put it all together, and essentially I'm just replicating what they have already done. So I'm not trying to tell you that I like figured this all out, I'm super amazing. It's just I went, saw what someone else did, say that's exactly what I need. The only thing I had to change out was the graphics card. We're getting the NVIDIA RTX 4000. I think is the one, or it's RTX 3000. It's either 3 or 4. I think it's the 4. Pretty sure it's 4. Which has real-time ray tracing, which means rendering and everything that SolidWorks does that's not CFD is going to be like super fast. And right now, when I do renders, it takes almost a day to do a video render that's like 5 minutes long. So that's going to be a huge time saver. And then with the CFD, with the 5 gigahertz overclock, we should be seeing times well below 1 minute. So wanted to give you this video to kind of cue up what's going to be happening. I'll do a video of the build. I'm very excited about that. I got to get the laptop all set up and transferred over. So kind of a lot of time sitting here in front of a computer again. Well, that's what I've been doing. But now I'll be transferring files and moving all this stuff around, getting everything all set up. So we got to get that all done. But I'm excited to have the big computer here and get it built. And then actually have it start chewing through all these different simulations, because we have hot simulations that we have to do, we have cold simulations we have to do, and then we have optimization, different material selections, HVAC decisions, changes, orientations, clear roof, non-clear roof, what if we had more lights in there, heat off the lights, all these types of things. Lots of different options to go into. So I want to simulate them all with the big computer, get that figured out, have that good information there behind me before we really pull the trigger on what size heat pump we have. In general, where we're at right now, I've actually met with our last supplier yesterday. That was Monday. And they're really excited to be working with us. We got 3 major suppliers working with us right now, and they're going through the designs, chewing through it all. There's 74 custom parts that they have to look at, so it takes them a while to get through all that. Starting to get feedback from them on some things that I need to change to make it more affordable in the long run, make it easier to build, which just helps everybody out. So I'm excited to get to that, but I can't get to those things until we get the thermodynamics taken care of, because the thermo will set up everything. If there's a problem in thermo, we might have a material change in some of the structures, for example, if they get too hot in the locations that we want to put these, because we like to be able to put them down in the deserts, which means it's going to get warm and toasty, so we got to make sure that they can withstand that. So very exciting though to get to all this. You can see lots of work. This spreadsheet, I've had 4 different versions of it. I've gone through all the equations, really trying to make sure I'm using them right. I think, like I said, within 4 degrees of SolidWorks is not bad at all when you're doing hand calculations of a very complicated, ooh, almost got him. Darn flies. When you're doing very complicated math, it's nice to know that the simplified versions are, within 4 or 5 degrees of what the big computer's getting, so that's not bad. Anyway, more videos come. You're going to see the new computer being built. We'll get the P53 set up, get it all going, and start chewing through some of these simulations. Very excited to get to this point. And yeah, we'll see you in the next few videos. So thanks for following along, everybody. If you like this video, if you like The Real Martian, what we're doing, be sure to give us a thumbs up. You can also check us over at eatinggrowsystems.com. Go over there and check that out. And oh, another little drop for my wife. She's doing great work over at theblossomingtable.com. If you like food, if you like inspirational messages, and you like eating healthy, go check her out at theblossomingtable.com. We're at eatinggrowsystems.com. We're getting that site updated, and we'll start posting some new information there. Also on Instagram at Eating Grow Systems there. But subscribe here to The Real Martian, because we're going to keep it real on The Real Martian. We're going to keep doing some cool stuff. The build is all going to be shown here. We're going to have a lot of exciting things, so tell your friends. Get into it. We're also on Patreon. I left my job, so every little dollar helps. If you'd like to contribute, really appreciate that. Thanks to everybody who has invested on our Friends and Family round. We've raised over $80,000 to go after this, so really appreciate that. If you'd like to be a part of this, if you'd like to invest, shoot me an email at trm@therealmartian.com. The link is on our page here, so always looking for people to be interested in investing. We're all in on this, so making sure that we get it right. when your livelihood depends on things, it's amazing how you want to make sure you get things right. It is like the scene in The Martian where he's like, you know, he blew himself up because he was stupid. You're like you don't want to do that in the real world, right? So making sure we get these numbers right is going to be really important, and we're putting a lot of time in that since I don't have a paycheck right now. So anyway, thanks again for following along. Thumbs up, hit subscribe. Don't forget we're on Facebook and on Twitter. In the meantime, this is The Real Martian. Out.